Welcome to the second session in the lab, which is about signal analysis and measurements. We will use the devices to send and receive a single carrier signal, and we will be doing different measurements on this signal for performance evaluation. We will see something like eye diagram, polar and constellation diagrams. Also, we will see how we use the spectrum of the signal to make measurements like signal to noise, power ratio, and other things as well. Starting with the first part in the manual, part A, we need to send an unmodulated signal using a coaxial cable connecting both VSG and VSA. We will control the VSG using this web UI, which has a panel that is very similar to the physical control panel on the device itself. If you are not familiar with this GUI or you don't know how to reach to it, you can revisit the first session of the lab. For the VSA also we will control it using a remote control software, though you can plug in a keyboard and mouse and control the device directly because it has its own screen and an operating system running there. Now here we see how we connect both devices using a short coaxial cable. We will send the signal at two different frequencies, but as we have the devices connected using a coaxial cable, make sure that you make these measurements with the help of a TA. First, we start by making sure that the RF transmission is off. Then we go to the frequency option here. We adjust the frequency value. Let's start with 600 megahertz. And for the amplitude, we will pick minus 30 dBm. Now the tune signal is adjusted. We can start transmitting. At the receiver side, again, we need to adjust the center frequency to 600 megahertz. And here we see clearly the tune signal. Let's put the band to 1 megahertz. Now let's do some scaling to see the spectrum in a better way. We can right click and choose auto scale here, as we see in this shape. Also we can do scaling for the y-axis by adjusting its maximum and minimum limits and the step size in between, in a similar way to the x-axis where we adjusted the center frequency and span. Also, we have something called range or reference level, which affects the attenuation applied by the VSA on the received signal. Instead of adjusting it manually, we can go with this option, which is auto range, which will change it automatically. Let me just bring it back to its original value. Now, for the main signal, we expect to receive a DC signal because we have an unmodulated signal, pure tone signal with a DC envelope, constant envelope as seen here. This fluctuation is due to noise. We can see it more clearly by decreasing the step size and also decreasing the maximum value here. As we see here, this fluctuation is due to noise. Now, to do some power measurements, we have something called marker here. Back to the spectrum, we put a marker on the peak in the spectrum, or we can right click and choose peak here, which will give me almost the same place. And here we see the measurement, which is minus 30.1 approximately dBm. Which is a very minor attenuation of 0.1 dB, because as you remember, we sent a signal of power level of minus 30 dBm. For the noise floor, we just also put a marker somewhere, but because we have some fluctuation, the measurement also will have fluctuation. To have a better view of the noise floor, we have something called averaging. So we can average these snapshots and see an average output. So to do this, we go to measurement setup and average, and here we turn on averaging, and we choose the number of snapshots to be included in the averaging. By choosing 100 here, I can run, and as we see here, these are the number of snapshots that we're taking and averaged out, and to give me this final result. Now I can repeat this process. Instead of doing it and stop, I can keep repeating here. As we see, it will keep averaging. Also, we can increase the number of snapshots to have a better view. And let me stop repeating. As we see here, this is the noise floor, and it says it's minus 81.15 dBm. Now here, when operating at a frequency of 600 megahertz, we have a loss of approximately 0.1 dB. Now let's send at a higher frequency, like for example 6 gigahertz, and see what would happen to the attenuation. Now here we adjust the center frequency again to 6 gigahertz. Let me remove the mark. And we run again, and we wait for the averaging. And we pick the marker again, and we put it at the peak. Now we notice that we have a received signal power of minus 32 approximately dBm, which means I have a path loss of 2 dBm, which is more than that loss at the frequency of 6 megahertz. We are asked also to find the power spectral density of the noise. To do that, we go to trace A here, and we choose, instead of spectrum, PSD. And similar to what we did earlier for the noise level power in dBm, we just put the marker on the noise level, and it will give us the measurement in dBm pairs. In part B, we are asked to send the same unmodulated signal wirelessly using the devices. As we see here, we have them connected to antennas. These antennas operate at a frequency of 460 megahertz. So we go to the BSG setup and we pick 460 megahertz. And for the transmission power, for fair comparison, we pick minus 30 dBm, and we start transmitting. At the receiver side, we also make sure that the center frequency is 460 megahertz and the span is 1 megahertz. To measure the received signal power, we pick a marker and we put it at the peak here, or we can right click and choose peak here, and it will give the same place almost. And as we see here, we have a received power of almost minus 49 to minus 50 dBm, which is a significant loss compared with the wired connection. As we saw earlier, at such operating frequencies, the loss is very minor. It's just portions of 1 dB, but here that was in case of wired connection. But here, if we have a wireless connection, we see that even at close distances, we have a minus that can be up to minus to 20 dB.